Information gain measures the expected reduction in entropy. So it's nothing but something which is already defined on entropy. So wherein we were actually checking for the entropy. Information gain is talking about the expected reduction in entropy or uncertainty. So entropy is basically the uncertainty. So we saw in the previous slide that it was highest at 0.5 when your x is equal to 1 was ranging between 0 to 1, right? So the probability when it was varying, when you were not sure as to what would be the value of x, that is where the entropy, that is uncertainty, was the highest, right? So information gain is a measure which does the opposite of that. So using entropy itself, so it is basically trying to understand the expected reduction in entropy. So obviously if you see, this would be very high when you are at the edges and very low when you are at, so it will be an inverted shape if you just try to take reference from the previous one. The formula is gain of x comma a is equal to entropy of s, which you computed over there, minus summation, right? And then it would be an absolute value of sv divided by s into entropy of sv, right? Now values a is the set of all possible values for attribute a, and sv is the subset of s, that is the entropy, for which attribute a has value v. Sv is equal to s in s, given the condition that a is equal to v. The first term in the equation for gain is just the entropy of the original collection S. The second term is the expected value of the entropy after S is partitioned using attribute A. So what is the information gain? If you use attribute A for partitioning, that is what is being measured, and that is the expected reduction in uncertainty. So if you have used a variable and then if the reduction in entropy happens, that is good. If it is not happening, that means the variable we have used is not really that great. So it is simple, the expected reduction in entropy caused by the partitioning of the examples according to this attribute. It's a number of bits saved when encoding the target value of an arbitrary member of S. So that's what we basically do in this whole thing. We try to increase the information gain, we try to reduce the uncertainty in the model. So if you are you're looking at something like whether a student will pass or fail in an exam, and if you are taking one of the x's, right, as in this case for the decision model, if you're taking one of the attributes like say number of hours of tuition attended, right? Now if that variable is not able to clearly reduce the uncertainty of the decision that a student will pass or fail, that means that is not having an exact influence on the pass or failure result. That means it's not a good variable, and that is what you're trying to test with information gain, reduction in the uncertainty. So that somewhere is used as part of the model. As an example, you can see on the screen that for a set of training cases, they attribute values for prediction or classification model. So it shows it in a tree based structure. So before partitioning, the entropy is in a structural form h 10 by 20 comma 10 by 20 is equal to minus 10 by 20 log of 10 by, divided by 20. The log over here is to the base 2, which is not shown. Minus 10 by 20 log to the base 2, 10 by 20 is equal to 1, right? Using the var attribute divided into two subsets. Now this is where it becomes conditional. So entropy of the first set, so the h for home is equal to minus 6 by 12 log of 6 by 12 is minus 6 by 12 log of 6 by 12 is equal to 1. Similarly, the entropy for the second set remains as this. The expected entropy after partitioning of the data is minus 12 by 20 into h for home plus 8 by 20 into h away is equal to 1, right? So using the when attribute divided into three subset, right? So the entropy for the first set, second set, and the third set is computed. Now you can see over there for the second set h 9 p.m. it's coming as 0. So the expected entropy after partitioning is totaling up to 0.65, as you can see from the formulation, and the information gain is 1 minus 0.65 is equal to 0.35, right? That's the actual information gain which you have achieved when you're doing three subsets using 5 p.m., 7 p.m. and 3 p.m. as a data point. So the decision knowing when attribute values provides large information gain than where. When attribute should be chosen for testing prior to the where attributes. Similarly, we can compute the information gain for other attributes. Obviously, you usually don't have just 2 or 3 attributes. You have multiple attributes which are considered when you're doing a decision tree. and at each node choose the attribute with the largest information gain. Now you wouldn't be doing this mechanically, you will be running some program like, say for example, a tree or rpart or C tree algorithm, right? So these algorithms will take care of all these things. You have specific decision nodes over there wherein you can say that, okay, if you're doing an rpart, that is recursive partitioning, so what is the parameter to be chosen? So are you talking about information gain, Gini coefficient, or which thing to be considered to partition it? So that will be taken care of. Now stopping rules, so as we had discussed, so if you don't want the tree to go very deep, we have to give some rules so that it stops before that, right? We don't want more of branching. So it's like something like your garden. So if you have a small bush and it's an ornamental bush which is used for just showcasing, right, and it doesn't have any usability apart from that, you basically chop the bush by giving it a good shape. So where to chop it, right? All these rules have to be given. So every attribute already has been included along the path of tree building, right? And you have to specify the stopping rules, like minimum number of elements to be present in a partition of data, beyond which, if it is there, only then the partitioning will happen further. If it is not beyond that specified value, it should stop partitioning over there. Now these things can be specified. You can even specify the entropy condition, or you can specify the information gain condition and all those things, so that your tree can accordingly be built. So for continuous attribute, each non-leaf node is a test, right? For continuous, that means for numerical variables, right? Its edge partition the attribute into subset. For a continuous attribute, partition the continuous value of attribute A into discrete set of intervals. So you can do a binning kind of stuff, right? Create a new Boolean attribute AC which looks for a threshold value, and based on that partitions it into true or false. You're just converting it. So if the value of AC is less than C, then you are saying it is true, otherwise it is false. We had done this something like this yesterday when we converted the Boston data, which was having a Y which was numerical, into a categorical form also, right? And then you have to select what value of C you will see. In that case, we had done a summary function, and we had said that if the value is higher than, say, the third quartile, and we were partitioning into a Y is equal to 1 in that case. Evaluation, so obviously you will be doing a training model building. You will test the model in a training data set also, you will test it in the testing data set also, and if you want, you can even have a third data set called as a validation data set. So when you're working as a consultant, you might do this, where you might build the model on a training data set, do your internal test on the testing data set, and when you want to do the user acceptance test, you might take the validation data set and do a cross validation over there, so that you are very sure that the model is performing. The strengths, it can generate understandable rules, perform classification without much of computation. You don't have to think about the statistical significance and all those things. Can handle both types of data, continuous as well as categorical, and provides a clear indication of which fields are more important for prediction or classification, even for a non-statistical person. Weakness, not suitable for predictions of continuous attribute because there is a lot of randomness in the data. Performs poorly with many class and small data. So obviously when the data is small, it's not the good technique to use. Computationally, it's very expensive to train a decision tree on a large data set, right? But obviously with today's modern platforms of distributed system, this is not a problem any longer, right? So traditionally, if you want to remove the problem of variance in case of a decision tree, you would use some techniques like random forest or bagging or boosting or something like that, but obviously those are computationally very expensive. But obviously with the latest infrastructure, these things are no longer a problem anymore. And also decision trees do not treat non-rectangular regions well. Now you need to understand the structure of these things, right? So if you're looking at data and if you're saying that there is a Y which has two forms, if you draw a line between that, and if it is clearly separable, that is where you would not use a decision tree, you would use something like the traditional algorithm. But if the data is in blocks or chunks, wherein you can see that I can create some rectangular blocks, that is where decision trees are good at, right? But if it is not in that form, a decision tree starts failing, right? So non-rectangular regions are not good for decision trees. So now let's come to something like an ensemble model. So it's pronounced as ensemble. which basically is nothing but a group of lot of trees. So basically these are not optimized trees, but what we do is instead of using a single strong tree, you use a lot of trees which are not optimized within themselves, but you use them as an ensemble. That means it's something like if you look at how furnitures are manufactured these days, right? So traditionally we were using something like a teak wood which was very strong, but in today's days we are using something like a reinforced kind of stuff. So we are using particle board, which is a combination of lot of weak things, right? Dust basically. We are using something like a ply, right? So when you look at ply, right, it's this thick, so you have different width. So it's just a layered approach of multiple wood layers which are very weak within themselves, but when you stick them together and pressurize them, they become very strong materials, right? So that is the same concept which is used in random forest. So I'm not using the best of the breed, but I'm using weak learning trees and combining them together, and the output which comes out of this in fact much better than what you would get for a traditional decision tree. And that is what random forest is all about. The name random comes over here because as compared to bagging, wherein you create multiple trees from the same data set again and again by doing the concept of out of box sample. So you say OOB, leave one out box and all those things, right? Over here in random forest, what you do is at each level, when you're doing the decision partitioning, you're giving preference to few variables to become important variables or partitioning variables, right? And that you are selecting randomly, right? And that is why it is called as random forest. Obviously it's a very big concept, and when you look at this from an application perspective, there are a lot of things which you should be looking at, right? But the random is coming because you are selecting or you are giving importance to a few variables. So if you have say 20 variables at one point in time, usually when it is a numerical variable, then you do a square root of the number of available variables, and if it is a categorical variable, you take 1/3 of the variable count, and that becomes a criterion that these many variables will be pre-qualified at every node to take a decision, right? So you take out of 20, say roughly 1/3, so 7, right? 7 variables will be first pre-qualified, right? And out of that, one variable will be finally selected to partition the data. Again, the same process will be repeated every time, right? So that is why it is called as random forest. And obviously because it is random forest, what happens is that you might be ignoring a few variables at some time, and that is why as compared to a bagging tree, when it comes to random forest, you have to have more number of trees. So if you are using 500 trees when you're doing bagging, you will have to use at least 1500 trees when you're doing random forest. That's how the basic concept goes, right? So what you are seeing on the screen is 5 to 100 trees. I would say you have to go more than that. It's beyond 500 trees which you will have to use when you're doing random forest, and obviously the computation will be very expensive, right? So the common default is to use square root of the number of attributes, right? Again, it depends upon whether the y is numerical or categorical.